Chemical kinetics, rate factors, and reaction energy diagrams. All right, so first thing we do is we look at the collision rate model. The molecules must collide. Well, it helps if I could write stuff in. I think you'd appreciate it. So the first rule is that molecules must collide. And the concentrations of reactants are decreasing while the product concentrations are increasing. The other thing that has to occur is you must have proper orientation between the reactants, which lead to a transition state, which results in a transitory species known as an activated complex. If it's actually a molecule, it may be referred to as an intermediate. And the collision must have enough energy to form the transition state and convert it into the products. This is a dynamic condition. Okay, the reaction proceeds with no net change in concentrations of reactants or products. So, for example, if you have 10 reactants and 4 products, and it's an equilibrium, then as the reaction proceeds, you can maintain 10 reactants and 4, I think I said 4 products. They may not be the same molecule because it may be going back and forth, etc., but it is the same number. Now, the collision rate molecule model operates is the interesting part is once you get the collision, you need the collision with the proper orientation. Now, what does that mean? Well, here we have the reaction of carbon monoxide and nitrogen dioxide goes to carbon dioxide and nitrogen monoxide. Okay? So if we notice here, what we're actually doing is transferring one of the oxygens to the carbon. So the oxygen on the nitrogen dioxide has to collide with the carbon to make the bond. So here you have 2 oxygen collisions. There's no bond here. Again, 2 oxygens colliding, no bond. You have the carbon and the nitrogen colliding, no bond. This is where the new bond would form. Now, there are variations on the theme for each of these, but this is just 1 out of 4 examples working. So this is actually pretty high. This says 25% of all the collisions would work. But if you'll notice, there would be a whole lot more variations. So when you talk about collisions, there are a whole lot of them going on where only a small percentage or fraction of them will occur. So remember, we talked about the nature of reactants and concentration, status, subdivision are factors that affect reaction rates, and we said that we come to temperature. So just a minute ago, we said that in the collision model, you have to collide with proper orientation and you have to have enough energy. Well, where do we get our energy? We get it from temperature. Okay, and this one's kind of hard to see. It may be easier to see here, but notice that it's brighter in hot water than in the cold water. This to me may be true, but this is kind of hard to see. So the net effect is the rates will increase with increasing temperature. When you do the kinetics 2 lab, then you will see this occur as the reaction rate. In addition, one of the at-home labs, you'll see this as well. All right, so let's go back to we have a higher temperature. Now remember, temperature for gases are a bell-shaped curve. Notice we always have some at 0, and we always have some really high up. But what we're talking about is the averages here, which is where the majority lie. Okay, so if we look at this, the energy needed for a reaction to proceed, we call the energy of activation. And remember, we talked about the fact that you had to have a collision occur with enough energy to get it over the hump. So this is activation energy. Well, if this is the minimum energy needed for the reaction, then any molecules that have that energy will react. Well, notice that for this one, you have this many. For the red one, you have this many. And the difference is this is the high temperature, red. This is the low temperature. So what you're looking at here is that you're going to always have a few particles with enough energy. But how many you have is a function of the average or the temperature distribution. So this is why in the winter, if you hang clothes on the line, yeah, they're going to freeze. But eventually they will dry because not near as fast as putting it in the summer, because the effect is that you end up with more particles having enough energy to escape. Okay? So the energy needed for a reactant to proceed is called the activation energy. Okay? E sub A or activation energy, or energy of activation, doesn't matter. Now this is a reaction energy diagram. So if you notice, we have energy going up here. We have reaction progress or time. Sometimes you'll see time here. And here are the reactants, and it is going up and over. This is the activation energy, is this energy here, because this item here is the transition state. And it's kind of like a hill. Once you get to the top, you can roll forward and you can roll back. Okay? So if we work a problem with it, the way we relate it is the Arrhenius equation. Now, remember, K is the rate constant. A is going to be the frequency factor. This is the collision frequency, or number of collisions, plus the probability factor. The probability factor is pretty much the orientation. Okay, so these factors combine to give you A. E sub A is the activation energy. R is the gas constant. And because we're dealing with an energy, the gas constant we will use is the 8.314 joules. I think it's moles K. No, it's joule moles K. No, yeah, it's joules per molarity to the minus 1. Okay, that's why I give you that value, because I can't remember squat. Okay. The units on that escape me, but it is joules. And the temperature has to be in Kelvin. All right. So if we look at this, if we know the rate constant and we know the temperature, we can solve the activation energy if we know A. And A is our problem child. So an easy way to determine this is to compare two temperatures with two rate constants, because the A factor will be constant and it will fall out. So what we're going to do is this equation here, or this problem here, reaction is a rate of this at this temperature and a rate here. What's the activation energy of this reaction? Well, if we compare two, we're going to get the natural log of K sub 2 over K sub 1 is equal to E sub A over R times 1 over T1 minus 1 over T2. Now, notice a couple things. You've got to keep K2 with T2 and K1 with T1, but K2 comes first with the natural log, but second when you're doing the parentheses. So if we sub this in, we end up with the natural log of 5.7 times 10 to the minus 2 divided by 4.3 times 10 to the minus 3 is equal to E sub A, which is what we're looking for, 8.314 joules per molar K, I think. I think it's moles K. I really got to look that up. Okay. Times 1 over, and this is where we have to have calculated. This is 285.15 K. This one is 299.15 K. So T1 is 285.15 K minus 1 over 299.15 K. All right, so what we see here is a lot of math going on. So we're going to take the natural log of the ratio, which is 13.2558, is equal to E sub A, 8.314 joules per mole K, times, and it comes out to be, this one is 0.0035069, and this ratio is 0.00333428. So we end up with a difference of 1.6412156 times 10 to the minus 4th. Now remember, I like to carry multiple values. More importantly, I really like to let the calculator carry them, and I don't write them down. So if we take the natural log here, we get 2.58446 is equal to E sub A times 1.9740385 times 10 to the minus 5th. So E sub A is going to be equal to 130921.26433. And this is joules. So if you use 4 significant figures, it'd be 130900 joules. Some people like to put it in kilojoules. It's still 130.9 kilojoules. Whatever floats your boat, as long as if you use it again, your units will cancel. So notice it's a big number. That's to be expected. Activation energies tend to be a little bit on the high side. Okay, the higher they are, the more possibility a reaction will not proceed. Okay, now I'm missing B. So I'm going to add one in because I need to do part B. All right, B says what's the energy, A for the reaction. So if you'll remember, K is equal to A, E minus E sub A over RT. Okay, so that being the case, we need to pick one of the two equations. Doesn't matter which one. I picked the first one, so 4.3 times 10 to the minus 3 is equal to A, E to the minus 13, 3, I think there are 4 zeros, 1, 2, 3, 4 zeros, yep, divided by 8.314, it's a joules per mole K, times the temperature, and we used this temperature before, so we've already done the math. Now, one trick here when you do E, remember E, the inverse, e to the x is, the inverse of that is the natural log. Okay, so just like log of x is equal to 10 to the x So 10 to the x is equal to the natural log of x. It's easier for me to work in base 10. So this is an aside. Also, it's easier to put it into your calculator if you go ahead and do the front math first. So e to the negative 54.835266. Now, it is critical that you keep the negative. Don't drop it because it'll get you in trouble if you do. So 4.3 times 10 to the negative 3 is equal to a to the 1.5323 times 10 to the negative 24th. So A is then equal to 2.80622 times 10 to the 21, which means it's 12.8 times 10 to the 21st. 81. Okay, so that's the value for A. And notice it doesn't have a unit, and that's fine. And it's not that this is difficult. It's really a function of two things: picking the right equation off of the formula sheet, and the second identity is to how to use natural log and E functions. And the ugliness or the beauty, E and natural log ln are used in the rate laws. Almost everywhere else it's base 10 and log. So just remember, with 14 it gets wonky. All right. So here we're back to a phase diagram. And remember, this energy is the activation energy. This is the energy of reaction. And so because this is negative, no, this is positive. Because here are the products, here are the reactants, and this is an endothermic reaction. If you were to have the products, no, that's not. Let me look at it. It's final minus initial. I was right the first time. Again, on tests, never change an answer. So this is an exothermic process. Okay, this is your activated complex right here. This is your energy of activation. This shows the potential energy versus the reaction energy. This is the reaction energy for a two-step process. And the previous one was a one-step process. This is a two-step process. Remember, we did reaction energy diagrams, actually, I think in chapter 5 in 1211. So this one is a two-step reaction energy. This one is endothermic because this is E sub A for the first. This is E sub A for the second. This is reactants and products, so this would be delta H, and it is positive, so this is an endothermic reaction. Okay, this is my version of one, and so you have energy, time. These are reactants, this is products, this is the activated complex. Okay, this line here is to be helpful if you go from the reactants to the activated complex. This is the E sub A of the forward. But if you have a reversible reaction, then this would be the E sub A for the reverse. Actually, E sub A for the forward starts down here at the reactants. E sub A for the reverse starts at the products. The difference between the reactants and the products is delta H. And in this particular case, delta H is positive, so this is an endothermic reaction. And down here, I have a note that says, put in the effect of a catalyst. So I will do that. I'm going to use that color for my catalyst. So what a catalyst does is we're going to go through this, but it's going to lower the energy of activation. So this is the effect of the catalyst. Notice that this would be the new E sub A. And so it lowers the energy there. Okay. This one, again, the effect of a catalyst. We'll go ahead and put that in. It lowers it. The example given in the text is for a two-step. It works on a one-step too. Again, activated complex. Okay, this one, on the other hand, is delta H is negative, so it's exothermic. It's my catalyst. Here's E sub A forward. Here's E sub A reverse. Here's E sub A catalyst forward. So you can, there's an old saying that says a picture's worth 1,000 words. And in a reaction energy diagram, you get a lot of information for a little bit of time, energy, and effort. Okay? So we have technically not done catalyst yet, but we're about to. But because I have the reaction energy diagrams here, I went ahead and showed you how a catalyst works. But we'll go into it in a lot more detail in the next section.